Greetings and welcome to another ReMBlock screencast. In this screencast we're going to continue our journey of investigating YAWL, and we will specifically be looking at how return, revert and keccak256 calls work in YAWL. So let's start off with looking at this function in this new contract called return example. And what we've got here is an assembly block, and it's very simple. All it does is use mstore to load 2 into slot 0 and 4 from slot or memory address 2, 0. So in other words, these are going to load 32-byte words into memory at these locations. So 32 bytes will be loaded here at 0, and then another 32 bytes will be loaded at 20. So that's 32 bytes into the memory. And then what we're going to do is return this area of memory. So from 0 all the way up to 0x40. So this is, of course, 64 bytes. So let's see this in action. What we can do is deploy this contract, and we can scroll down and look at return example, which is here. And you can see that it returns the expected values 2 and 4. And it does this because it's returning this area of memory, which is 64 bytes. So in YAWL, it doesn't matter in terms of types. We always deal with 32-byte words. And when this gets this will basically leave the assembly block and send it back to the function, and the function interface specifies two uint256-bit numbers, which is why these get translated back to that for the client. Now, if we want to revert in Solidity, we would use the revert keyword. Now, revert and return both can return some data, but most commonly you don't return data with revert. What you really want to do is end the execution and revert everything back to the original state. So here I've got two examples, one written purely in Solidity and one using assembly. But both of these functions essentially do the same thing. They require that the sender of the transaction is this address, otherwise it's going to revert. Now, the way it's done in Solidity is probably very familiar to everyone, and assembly, it's slightly more low level in the sense that what you do here is we check for is 0, that the equality of the caller is this. So we've got this equal function, EQ, and we've got this caller which will return the address. So a caller is the same as message.sender in Solidity, and then we just check, are these the same? So that's what equals does. And if they are not the same, then it will return a 0. So equal will return 0, which will make this true, and then it will revert. So let's see this in action. So if we look at the require Solidity, we can see that, let's just check the address that we're using. Let's move back to this address here actually. So notice the address is AB8CB2. If I call the function require Solidity, we're going to see a revert. And if we call require YAWL, same thing. But if we use the address specified, then we will not see a revert. We'll see the transaction go through. So that's how to use revert. And the final example I want to show is keccak256, how we will hash data using YAWL. So here's the way we do it in Solidity, which is to basically we need to pass in some ABI encoded data that is already in memory into the keccak256 function. So the way we do that is we use ABI encode to basically load the data we want to hash into memory. So in this case, I'm loading 321 into memory. And remember, these are going to each be 32-byte words that are stored in memory. So this will take up 32 bytes, this will take up 32 bytes, and this will take up 32 bytes. And we store that in this data variable here, or reference it to the location in memory, and use that to perform the keccak256. Now, of course, we could just put this directly in here, and we don't need to do that. But I'm just showing this so that it's clear that we are actually pulling this out from memory. Now, the way we do this in a more low level way in YUL is like so. It's a little bit more involved, but I think it's clear based on what we've seen so far. So if we start off with loading the free memory pointer into this variable PTR, remember the free memory pointer is always starting at 0x80, and the value of the memory pointer is always stored at 0x40. So when we start, the memory has 0x80 in this memory slot, which is the location of the free memory pointer. All right, and then we start to store our data directly in memory, which is essentially what the statement here is doing, but we're doing this in low-level assembly. So we're using mstore, and we store at the free memory pointer, which remember will be 0x80. So at that memory location, we're going to store 32 bytes to store the number 3. Then we're going to store at the next 20 bytes, the next 32 bytes over at, so we add the 0x20 to the pointer and we store 2. And then we add another 32 bytes and we store 1. So what we have, again, is going to be a contiguous block of memory with 3, 2, and 1 all stored in the memory, each one taking up 32 bytes. Now this is just good practice, we don't need to do that here, but we're updating the free memory pointer such that it now points to the next slot which is available for writing to the memory. So we do this by updating the free memory pointer, which is located at 0x40 in memory, and we add to the pointer that we loaded the block of memory that we already wrote to, which is 96 bytes or 060 in hex. Finally, we want to take the keccak256. So there is the keccak256 function available in YUL. You can see it in the docs here. So as we can see, what it does is it takes the location in memory that we want to hash and then the length of the data that we want to hash. So what we do here is we pass in the pointer. Remember, this has been unchanged, so it's still saying 0x80, which is correct. That's where we started writing our data. And how much data do we want to hash? We want to hash the 96 bytes that we wrote to memory. So that's what that will do. It will return the hash of the 96 bytes stored in memory at this location, and it will store it at address 0x00. This is the so-called scratch space in Solidity. It's a piece of memory that's right at the very beginning. In fact, it's the first 64 bytes of memory, which we can use as scratch space for exactly this kind of purpose, where we just want to store a value, the result of a hash function, so that we can then return it in the next line, which is exactly what we do. We use the return keyword and we return the data that is in this memory area, so from 0 to 0x20, in other words, of course, the 32 bytes. So let's check that these two functions return the same value, because they should do. So if we hash in Solidity, we get this, and we hash in YUL, we get exactly the same value, as you can see. Now, interestingly enough, we can specify the data type here, but we are able to change how much data we're returning, and this might mess with the client. So let's take a look. If we only return 16 bytes, let's say, so let's clear this out and redeploy and run that function, so hash YUL, we're going to get a failed to decode output error, and that's because the client is expecting, as per the ABI, a bytes 32, but we're only returning 16 bytes. So this will break clients, so be careful and be wary of that. Now it's also worth noting that if we return more than if we return more than 32 bytes, so I need to redeploy this to show you, then it actually doesn't make any problem for the client. And this is because the client basically takes the first 32 bytes of the data and discards the rest. Now obviously you want to make sure that you don't do these kind of things in YUL, and you always try to map what you're returning to the data bytes or the type of data that you want returned. So just be wary of that you can break clients if you return too few data bytes, and it doesn't actually impact the client if you return more, but there could be other consequences. So I hope that helps to show you how you can use the return, revert and keccak256 functions of Yawl. For more details, of course, please refer to the Yawl documentation. Everything is in here to help you and make use of Remix to your testing. So I hope you enjoyed this video, and I'll see you in the next.